所以我今天要讲的是 Chiral kinetic model study of chiral magnetic and vortical effects。所以跟我以前两次讲像，我是 review 我自己做的东西，所以没有 review 很多的东西 ，right？ 所以 the talk will cover getting an introduction, then follow with chiral kinetic model, chiral magnetic wave, chiral magnetic effect, the spin polarization, and the chiral vortical effect. And all those work mainly in collaboration with Yifan Sun, and also lately working with Shuai Liu. And let me see, I go to the next page. And I always like this results by Xu Guang Huang. I think that he published a nice paper 2012, show the lifetime and strength of electromagnetic field in heavy-ion collisions. So to the left, so you will pay attention to the magnetic field. So this is the magnetic right curve. So it reaches very large values, about 10 pi square, but a very short lifetime. If you parameterize by this form, then the lifetime is about 0.65 Fermi. It's very, very short. And later on, I think there's another nice paper by McNaron and Skokov, tried to follow up with initial this magnetic field generated by the approaching nuclei. They assume the quark-gluon process immediately produced, then found the conductivity in the quark-gluon plasma. Then they can calculate how long the magnetic field life can be extended. So if one uses the lattice conductivity, that's a 5.8 MeV or so, if at the critical temperature of initial temperature a little bit higher, so it's about twice. So you at most get about 12 MeV. If you use that lattice conductivity, of course, it can increase the lifetime a little bit, but the magnitude is still very small. So that's 0.1 instead of 10, right? So that's still factor 100 smaller. And the NAS, you increase the conductivity in the QGP by a factor of 1,000, which is the blue dashed line. Then you can have a long-lived magnetic field that will make everybody happy. Unfortunately, we know this is contradictory to what we know about the QGP. The QGP is strongly interacting. Once it's strongly interaction, you must have a smaller conductivity. You cannot have both. You can have a strongly coupled QGP and a large conductivity. That cannot happen. Therefore, unfortunately, magnetic field lifetime in ultraviolet heavy collision lasts very, very short. Right? And once you have magnetic field and electric field produced in heavy collisions, and many interesting can happen. You can construct this vector current and axial vector current. Vector current we're familiar with, right? Just either charge or a baryon number and so on. The axial vector current is you separate into right-handed and left-handed currents. The difference is the axial vector current. And then if you have those currents, then those currents can be generated by electromagnetic fields. Normally, we have almost no electric field generate currents. Now, once you have a magnetic field, it can generate currents, charge current, if you have net axial charge in the system. Right? And also, electric field, once you have axial charge in the system, then electric field can also generate axial current. And also magnetic field also can generate axial current. So that's a very rich physics in quark-gluon plasma if it's subject to electromagnetic field. Because in the quark-gluon plasma, if the current quark mass is still very small, right? So this can be carried by right-handed and left-handed quarks. And another nice paper I like and always enjoy reading is the paper by Jinfen Miao and Zhi Weiling, and I think that's a student of Jinfen Miao. they realize in heavy-ion collisions, the vorticity field is very strong. So they use NPT model to do the calculations. So you calculate the vorticity. So that's the non-relativistic vorticity. You calculate its average value in the produced quark matter. Then you see how it evolves in time. So depending on impact parameter, if a small impact parameter, that's small, the vorticity, right? If got a larger impact parameter, the vorticity is very, very quite large. That's a big factor 50. And the point difference, different from magnetic field, is a lifetime is long, right? So you see the lifetime, even go to the half, it's close to 1 Fermi. So the lifetime of vorticity field is almost factor of, let me see, what's this one? 0.06. The other, it's almost 1. So you're talking about almost a factor 100 in lifetime. Right. And also, although it decreases with squared S, so you look at squared S is large, it decreases, but decreases not much, only factor 2 or so. So the point is, the average vorticity field produced in heavy-ion collision in a central collision is large at a long lifetime. And that's interesting because vorticity has a similar effect like the magnetic field, as you can produce. So that's in the magnetic field, you generate chiral-magnetic field, you have a chiral-vertical effect. So vorticity can generate current if that's an axial charge in a system, and also has this vertical separation effect. Omega also can induce axial current, right? So that's very similar to the chiral separation effect due to magnetic field. And of course, one would now we know the standard model in heavy-ion collision is described by hydrodynamics, particularly visco hydrodynamics. Therefore, ideally, one would like to develop hydrodynamics, including spin degrees of freedom, to include the vorticity field and also the spin of the particles, and also including anomalous effect due to the magnetic field. Unfortunately, those hydrodynamic models are not available yet, being developed by many people. So a couple of years ago, we just started with a kinetic approach because there are many people working on kinetic to try to derive kinetic equations to take into account the magnetic effect field and the vorticity field in heavy-ion collisions. I think many people in China are working on that, right? Wang Qun and his group, and Xu Guang and his group, and also Penfei Zhuang and his group. They're among the most active people try to derive chirokinetic equations based on variety, mainly based on the Wigner functions approach. And in the simple case, for the massless particles, then the distribution function for right-handed and left-handed, the quarks are given by this set of equations. They are too complicated. I'm not going to go into it. The point that we are only into the two cases. In one case is only we have magnetic field, right? Then the motion of the particle, right? Its velocity is given by this expression. P is the unit vector of the momentum directions. Q is the charge of the quark. B is called the barrier curvature, which is the P hat divided by P squared. Essentially, that's the vector potential in the momentum space. So magnetic field affected the velocity of the particles, and this also affected the momentum of the affect the position of the particle and the momentum of the particles. And the lambda is helicity of the particle. It's a right helicity and left helicity and so on. So this is the related effect of magnetic field. If you are interested in only the case of the vorticity field, set E and the P to 0, then those equations are modified into this one. Somehow the position evolves according to that formula. So depend on the vorticity field and also the Barry curvature. And the lambda again, it's the helicity. In this case, the momentum remain the same, right, during the free propagations. Of course, to really have a chirokinetic approach to heavy-ion collision, we can not only need those propagation, the velocity, in a way, this is like a velocity part of the both of transport equations. We need the collision term. So I should add a collision term on the right-hand side. And so one have to include in the two-body scatterings. But in two-body scattering, we all know involve the distribution function, right-handed quark distribution, left-handed quark distribution, and so on and so forth. And because of this term, right, because dt d tau is not equal to 1, right, and that modify the phase space distribution function. So what the equilibrium phase turns out equal to square GFP square G is that factors, right? Is this factor over here. And so I have to construct a way to make sure when the system reaching reaching thermal equilibrium and there's constant omega and the constant B, one should reach that equilibrium distribution given by that one. For that one, have to modify the collision term. That's a way to do it, invented by Evenson. I'm not going into the details. And of course, we know, especially we're interested in strange quark, and the strange quark is not really massless. So of course, the people have derived the chirokinetic equation for massive particles, and that we haven't adopted yet at those times. So we can do a very simple, assume a simple thing, just replace the unit of P by the velocity and the P by the energies, and the P over P squared by P over EP squared, right? Qualitative take into account the finite mass of strange quark. Now with this modified quark scattering, one can reproduce the V2 measured in Stark experiment very well. This shows the V2 as a function of PT, differential V2. Those blue dots are star data, and the solid line is from chirokinetic calculations, right? If one uses sufficiently large quark scattering cross sections into modeling the fact the quark-gluon is strongly coupled system. Of course, the three topics I will mention, hope I will have enough time to cover them. One is the chiromagnetic wave, the other is the chiromagnetic effect, the third one is the chirovertical effect and the lambda polarizations. So chiromagnetic wave is due to the fact, because we know the magnetic fields affect the right-handed particle and left-handed particle differently. So you have this right-hand current depend on the chemical potential right-handed particles, similarly from left-handed particles, right? So from here, you can derive, once you have this equation, then you can derive this wave equations, right? So how the density change, then you have this one, right? So separate the conserved vector charge of body on the right, and then can lead to these equations, right? So one is plus, the other is minus, right, left. Then you can do the linear small deviation, and you can generate a wave equation for how to say the density of the right hand, left hand, they change, evolving, change in time. And then you have this wave vector here, right? So how this is essentially related to the restoring force, right, over there. But the picture is the following, right? So because of the presence of magnetic fields, if there's a net charge in the system, right? UV, of course, V is a vector charge. In here, which is just an electric charge. If it's greater than zero, then the chirokinetic effect, the right equation, then you can separate right-handed and left-handed, one move up, one move down. So that's the chiral separation effect, right? One of those four equations. Then follow chiromagnetic effect. the second equation of those four interesting physics, you can generate a quadrupole moment, the positive charge here, positive charge here, negative charge here, right? Therefore, when after hadronizations, then the pi plus will go that way, pi minus will go that way. So this is a transverse plane. Therefore, that tells us the negative charged pion will have a larger V2 than the positive charged pion. So that's a very interesting idea. If experimentally one can measure the positive charge, the flow of pi plus and the pi minus, if one sees some difference, maybe they are due to chiromagnetic wave, right, in the presence of magnetic field. Of course, for this to happen, we need, for this to develop, we need sufficient non-lifetime for the magnetic field. Right, and for the charge, of course, we can get it by fluctuation. So although we know on the average, the produced QGP is charge neutral, but the event by event fluctuation. So that's fine. Yeah. And of course, experimentally, the V2 splitting between pi minus and pi minus be measured. And here's the data. So you define so V2 of pi minus is the pi plus, and A plus minus is the pi plus number, my pi minus just charge asymmetry. Then this slope, how the V2 splitting is a function of this A plus minus, that we call slope parameters. So here's the measured slope parameters, a function of centralities at the different energies. And you see that indeed that's splitting, right? And you have to fit that splitting, right? And in terms of simple chiromagnetic wave pictures, one needs this green line, which is the magnetic fields with a lifetime of tau equal to 4 Fermi, right? And of course, that's questionable. The reasons that we know, if you based on the initial magnetic field generated by initially bombarding nuclei, the lifetime only above it's only 0.66 Fermi, so it's almost 100 smaller. So the question, how do you get that for Fermi over C? Right? And also that's very nice, interesting work by Ko Liang. What he did is he used an MPT model. He artificially put it by hand. See, initially the proton distribution include the positively charged proton over here, positively charged proton over here, negative proton over here. It's artificially generate that quadrupole charge distributions, right? Then he ran an MPT, use the collisions to generate that chiromagnetic wave to get that V2 split. So indeed, he can fit the data. So the data is given by this gray band, and they can fit the data with that open square circle roughly, right? So it's about 2%. If it's a 2% quadrupole distribution in the charts, then he can reproduce the data. So that's very nice. So again, let's assume some of that quadrupole charge distribution can be already developed. In his case, they are immediately developed. And that initial charge then refract into the V2 splitting between pi minus and pi plus. So the questions, can those quadrupole moments develop so quickly, right? And right, we know in this figure it takes time to develop the quadrupole moment from here to here, right? During that time, you need a magnetic field. So what Ko Liang assume it's developed right over here, right? So that's why we try to look at in chirokinetic approach, right? We solve the chirokinetic equations, which automatically including all those four effects, those chiro with magnetic field, and then both the chiromagnetic effect and also chiral separation, they're all there, right? So what we did is indeed we can generate a V2 split. So in this case, we assume magnetic field is large, say 7 pi square. Lifetime is very long, 6 Fermi C. That's very, very long, right? Then indeed you can develop the V2 splitting. right? And indeed, you can get that a plus minus slope dependence, like what Guoliang obtained, right? But this requires very large magnetic non-lifetime magnetic field, right? That's one problem. Another problem is, right, if you want including the Lorentz force, then this V2 dependence on the A charge changes sign. And the story is can be explained, but it's too complicated. I will probably skip it. Intern, you can read in our papers, right? But in the derivation of the current magnetic by the schematic way in the paper, they neglected those Lorentz force. In Guoliang's calculation, he didn't address those things. He assumed quadruple charges already present in the initial state of the coagulon plasma, right? Here we have to generate dynamically by the non-lifetime of magnetic fields if there's an initial charge asymmetry in the coagulon plasma. Right? So anyway, my point is the chiromagnetic, that seems no evidence yet of chiromagnetic, although the signals consistent with chiromagnetic wave, whether it can be explained chiromagnetic wave is still not settled. Let me skip this one. Why Lorentz force changed the sign of the slope of the V delta V2 versus A plus minus. So after this chiromagnetic wave, let's turn to chiromagnetic effect in isobaric collision. The reason that they originally looked at the chiromagnetic effect in gold-to-gold collisions, and there are a lot of discussion whether it's a signal or not, and there's no conclusion, not a background effect. So people come out of this very nice idea, look at isobaric collisions. You have zirconium, the ruthenium, they have the same atomic number but different charge. I think the zirconium has 40 protons, ruthenium have 44 protons. And therefore, if we look at this figure to the left-hand side, the magnetic field, right, stronger in the ruthenium case than zirconium case. So hopefully that difference in magnetic field can generate a difference in the signal chiromagnetic effect signals. Now, this signal is defined as following, right? You look at the two charged particles of the same sign and up sign, calculate these correlators, and the difference, according to the calculations, right, will lead to this splitting. So that's not a very large splitting. We're talking about 10%, 10 or 15% effect, right? And it's due to the interplay of this one, because when the magnetic field, if you have mu5, remember mu5 is the axial charge. You have net axial charge in your system, then can lead to current, and then it depends on the charge. So the positive charge, negative charge will flow different. So that's little charges, right? So the equal. So in one side they have all the same sign charge. That's how to move either up direction or lower direction. They separate it, right? And in these calculations, I think they assume the axial charge density is of S is 0.1. That's huge, because S in the coagulon is probably 10, then 10 per cubic Fermi. So that's an NS below one unit of axial charge, right? That's per cubic Fermi. That's pretty large. Okay. So we did a similar using the kinetic approach to calculate. I think the previous using the kinetic, we just do it. Then of course we have to put in by hand the axial charge in the system, and we'll have a way to generate the axial charge in the system. Then the kinetic equation to take care of the dynamics. Then you can again to calculate those two correlates, up sign charge minus similar sign charge correlator like I showed in previous slides. And then, of course, if magnetic field long lifetime, then you see the difference, right? You see the difference. And we only see the difference if we use the reaction plane, not the event plane. Reaction plane means we calculate everything based on the initial reaction plane. This event is the physical, so then somehow washed out. And so at least and this result, I think, similar to I think that's Jim Fen's calculation using anomalous viscous fluid dynamics. I think couple of fluid dynamics with those coupled to the chiromagnetic effect to see how that develops in time. Right. And that's another correlator introduced in the Lacey. He said, let's look at delta S correlator. That means I pick up positive charge particles. That's a reaction plane angle. I take the sign, right? Calculate the correlate, divide the number of positive charge particle, same with next charge particles. So that's going to go delta S. So you do the one event, then you see how that delta S, right? You just see the distributions. So that gives you this N real, right? And then the unshuffle, that means you just randomize those particles, right? Just for normalization purpose. Then divided by something, you just artificial the psi at 90 degrees to do it anyway. If you do this, if it is off correlators, then normally you see this kind of behavior. Normally have this kind of behavior. And they are supposed due to chiromagnetic effects, right? And then the difference between the two is a tiny difference. See, over here, there's also a tiny difference. So again, this is based on non-leaf magnetic. Fortunately, I didn't put it on the lifetime magnetic field. I think we use something like 0.6. Yeah, I have 0.6 from university. And also very large initial axial charge density. Okay. Now let's see what's happened experimentally. That's a recent paper from Starr, and I think published this year. And I look at the chiromagnetic effect with isobar collision at 200 MeV by Starr collaborations. There are many ways of doing it, right? This so-called isobar blind analysis. I'm not so familiar with detail how to do it. Now the point is that there are many groups that did a variety of analysis. One's using the gamma correlator, the other is R correlator. This one I think is R correlator. Most the other gamma correlators. Then we have the solid and open circle, the solid square and the open. That's an open symbol, and one is from data. The other one is they call it from the expected one, right? So if you take the ratio to 1, then you get. Then that means that's a chiromagnetic effect. But since they're all below 1, therefore no predicted chiromagnetic signals observed in the blind analysis. So it's written here. The chiromagnetic sensitive observer ratio below unit leads to the conclusion that no predefined chiromagnetic signatures are observed in this blind analysis. Therefore, so far, there's no evidence for the observation of chiromagnetic effect in heavy ion collisions. I think before I go on, let me comment the reason, because to have chiromagnetic effects, you need 2 important physical input. One is the non-magnetic lifetime. The other is a large topological charge in the produced quark-gluon plasma leads to axial charge fluctuations. And we know the lifetime is unlikely to be long. And also we need a large topological charge, which probably cannot be very large. And so both are not in favor of chiral magnetic wave. Maybe they should be there, but the signal is just too small to see it, right? Now let's turn to lambda polarizations. Okay, that's probably more promising. Of course, we all know our good friends, so Tang and Xinyan, they were the pioneer in suggesting lambda was polarized in heavy-ion collisions. And they wrote a paper in 2005. 2 years later, Sturm published a paper on lambda polarization consistent with zero. After that time, the error bar is large and also other reasons. But after 10 years, start indeed to see lambda polarization as a finger squared S. So they have 2% polarization that's appreciable. And both are consistent with the two nice calculations. One is by Picatinny based on hydro, another by Wang using an MPT model. And in the hydro, then at the kinetic phase out, you can calculate vorticity. From the vorticity, you know what the lambda polarizations. That's what they get, right? So for the Picatinny's calculation, I think it's given by the blue line. I fit the data pretty well. And with this Wang's calculation, he ran MPT after hydronization and look at the hydronic method. Then he calculate local vorticity is called screening method. Then from what's the nodal vorticity, then he can calculate the polarization of lambda. He gets this dotted curve if including the fit down effect. So also agrees with data because the data has a large error bars. Right? And about similar time, we also try to look at the lambda polarization in the chirokinetic approaches, which is to follow the chirokinetic in the absence of magnetic fields and electric field, only have omega, the vorticity field, right? So what we did is we do the calculation. I didn't see, that's the centrality, right? So the centrality, therefore, then we know there will be vorticity field generated. Then we just follow. In a way, we do kinetic freedom. Not going to do the NPT. The only thing the NPT, you do not follow spin degrees for freedom, but in chirokinetic, we do follow spin degree of freedom. Since although we are working in the mass limit, you know the spin pointing in the direction of the momentum, right? Either around the momentum or the opposite of the momentum, according to whether it's right-handed or left-handed, right? So it's automatically spin is including the chirokinetic, essentially just the direction of the momentum. So you're doing that, we indeed find the global polarizations that can develop very, very quickly, right? And get a 2 or 3% like measured experimentally. That's for the quarks, right? The point is it can develop very quickly. So that's about the 1 Fermi. But what I mentioned, the lifetime of vorticity field lasts about 1 Fermi over C, more than 1 Fermi over C. Right? So that's not understandable why you can develop large vorticity, which translates to the polarization of the quarks. Right? It's very different from magnetic field. Magnetic field will just dies out after very, very short time. Right? Now, we also follow the idea of Zhou Tang using the coalescence model to convert the S quark into lambda. So to the coalescence model, you have 2 light quark, 1 S quark. It's a phase space distribution function, super lambda Wigner function is a Gaussian coordinate momentum space. And then you go to the relative coordinates. And then you just evaluate that integral to get the lambda, right? But this just gives a total number, lambda number. To get the spin, we have to include in the spin of the light quark and also S quark. So that we do, we have to say what's the probability for 3 spin half the quarks, including S quark, into lambda spin. But in the quark model, we know the lambda spin is entirely given by the S quark spin. The reason is that two light quarks form a spin singlet, right? So that's the, wait a second, yeah. No, there's two light quarks, okay, sorry. Lambda spin determined by the set. So UD quark form a spin singlet, right? So that is the, that's one's a U quark, the other is a D quark, right? So you can form spin. No, wait a second, I messed up. So this is the spin singlet, right? And let me see, just a second. Oh yeah, here, theta one, theta the other. There's a typo. Oh, there's a typo. Yeah, theta one, phi one, theta the other, polar angle of UD quark spin directions. So those two spin UD quark. So they can have both point in one directions, one point up, one point down, and they're both are pointing down. So that gives you the light quark. Then you have to take an overlap with to project into spin singlet. So in the quark gluon plasma during hydronization, I pick up a U quark and D quark. I know the momentum, therefore I know the spin directions. Then I can right, and so I can construct the probability for both spin pointing the same directions, both spin pointing the opposite directions, and one up and one down. Then I project them into a spin singlet. So when you work that algebra, the statistical probability for two, one U, one D, and one S to form a lambda spin half is equal to 1/4, 1 minus the helicity of the first U quark, helicity of the D quark, times the momentum unit vector dot into momentum unit vector of the D quark. Right, so that's just straightforward. One can calculate from the information from the chirokinetic calculation about the momentum of UD quark when calculate GS. Then from here, I can calculate the lambda number. Right? So indeed, after converting the S quark polarization into lambda polarization, we get this result, right? So there's a star data, there's other calculations, so they are quite reasonably well. And we also look at transverse momentum of lambda polarization, right? And it's flat. I don't know, I haven't compared with experiment whether it's flat or not. And at that time also predicted the repeat dependence, right? So the global polarization is peaked at the y equals 0. I'm not so sure what's the present status. I think there are other predictions. They claim the polarization of lambda will be larger rapidity, right? And I don't know what's experimental status. And I'll be interested to check whether this prediction is right or wrong. And of course, that's another puzzle. There's a slight difference between lambda and lambda polarization. And I think I skipped that one at this time. There are many explanations how to understand the slight difference between lambda and lambda polarizations. Of course, one of the most interesting is the longitudinal spin polarization. That means you don't look at the spin polarization along the y direction, negative y direction, that's a perpendicular reaction plane. You look at the direction which is along the beam directions. So according to Beccatini's calculation 4 years ago, 3 years ago, the azimuthal angle dependence has this shape, right? So here's the negative, positive, negative, positive. And that's calculated according to the thermal vorticity. There's a definite thermal vorticity, velocity divided by temperature. Then you take the full derivative, take a minus sign. Once you know the thermal vorticity, you put this formula up here. Then you can calculate the polarization. All right. And for this polarization along the z direction, beam directions, this can be simplified into these expressions. dt d tau, 1 over mt, t is the temperature, v2 is the v2, right? So that's the well-known v2, that's the sine 2 phi, right? So that's a sine 2 phi here, right? And now sine v2 phi has this behavior, that's a sine 2 phi, right? Let me see. PZ, this one, this is a sine 2 phi, that's a sine 2 phi, right? So factor 0 is 0, and I go to negative, then wait a second, yeah, and go to the sine 2 phi. No, the positive 2 phi. You have to reverse the positive 2 phi. Unfortunately, because dt d tau, the temperature decreases with time, therefore this is negative. Change this sine 2 phi, you get this shape. And that is consistent with this shape, right? So the first quadrant is negative, second quadrant positive, third quadrant negative, fourth quadrant positive. Unfortunately, experimentally, observations here, the first quadrant positive, second quadrant negative, so wrong sign. Similar result obtained by Jung Wang using a PT model, and look at the PZ, they also get a similar result, right? Wrong sign. And although they get the, right? And I think both are due to this dt d tau effect. Right? And I think at one time Jung Wang was mentioning that it may just drop this fact, assume there's no such factor, then you get the right sign. Right? They're called the kinetic, thermokinetic versus kinematic velocity rather than thermal velocity. In other words, when you take the derivative, you take the temperature out, right? Now we did also similar thing using the kinetic, chirokinetic approach, and we realized in that paper from Jung Wang's paper, we realized if you look at that, this is transverse plane, right? That's the in plane, that's the outer plane. Then you look at the vorticity in the transverse plane pointing in the x directions, right? So that's omega. So that's omega. So that's your omega, right? So omega x is this one, clockwise. Here the omega x is positive, so counterclockwise. Because this one, so omega try to push the X-ray charge into this way. So you have this, right, we look at the Z greater than you have a positive, more right-handed than left-handed, more left-handed, right-handed, so this one, right? So if somehow, if this one is important, then this is a right sign, right? So compared to the smooth angle, if it's omega, this X related to that, right? Because the omega X is pointing in the Z direction in this way. So you follow this right-handed rule, right? So you point in the negative Z direction, Z direction. So that's a chance this will lead to the right smooth angle dependent of the P of Z, right? Indeed, when we did the chirokinetic calculation, even obtained the following result, right? Here, look at this, right? The three component, right? So this is the omega y, which is negative. We know that omega y is negative. Omega x is positive. And that's another omega z is very, very tiny, right? So omega y is pointing in the y direction. Omega x is the point the x direction. Omega z is point the z directions, right? So that's small. This is positive. This is negative. So there are central cancellations. So when you add them all contribution to PZ, then you get these possibilities, right? If you only including the omega x contribution to PZ, then you get positive one. You get in the first quadrant. That's a first quadrant. We won't get first quadrant, positive quadrant. If you only including the Py, it's negative. So it's a competition between Px, Py, or omega x and omega y, All right, I only showed omega s in the other slide. But anyway, that's the run to the end, right? So the total PZ can be negative, and it changes into positive eventually. And then you look at the smooth angle dependence of longitudinal spin polarization, then you indeed get the right sign, right? Instead of negative here, you get positive. In positive here, you get a negative, right? So that's where, right? So it's opposite sign from those based on thermal vorticity, right? And of course, in our calculus, we even found out whether it's positive or negative, depending strongly on the interactions, right? If the parton mass is large, you get positive. If it's very weak, then get negative. So that's consistent. We know the parton must be strong to have a strongly coupled KGP, also larger V2. So that's consistent with the observed larger V2 in Beijing collisions. And I think after that, Chiral joined us to, here is the questions, is that in our calculations, somehow we never pay attention to angular momentum conservation during parton scattering. We never address the questions, right? So he tried to see how to incorporate the total angular conservation during the parton scattering. Therefore, he introduced for massless particles, then you need the so-called side jump effect. In other words, you want to adjust the relative distance between the pull particle before and after collision in order to conserve the total angular momentum, including the orbital and the spin angular momentum. So in that case, he introduced the covariant for the angular momentum tensors, right? That's the normal orbital part, that's the spin part, right? Since I don't think I hope I have enough time, okay? And the spin parts, you can go to, if you go to the rest frame, then there's a typical spin part. The spin will point into the momentum directions for massless particles, depending on the helicity, right? But in general frame, it has these complicated expressions. And then you talk about Lorentz phenomenal transformation. So you're trying to change how the total angular momentum changes, how the momentum changes, how the position changes, in order to have a consistent Lorentz transformations. He needs to introduce a side jump, right? After collisions, right? And the relative distance between two massive quarks before and after scattering, that's a difference in the relative. Suppose initially the two quarks separate a certain distance in space-time. After the collision, they separate different positions in space and time in order to conserve the total angular momentum J medium. That's the idea, right? And his total angular momentum tensor is given by that one, not only including the spin part, also orbital part. Therefore, the right-hand and left-hand current now have two contributions, one from spin part, one from, no, that's related to that this just related momentum because the spin point in the momentum directions. They also have this part, right? Because this is derivative, so they're related to the orbital motion of those particles. They also call them magnetic moment part, right? Then from there, then you can calculate the polarization just taking the exit current, right-hand minus left-hand side, then suppose we have the y direction, the global polarization, that's the y directions is calculated. And then he showed indeed in this case, one can convert orbital angular momentum into spin polarization through the vorticity field. To illustrate that, he constructed a simple box case, a simple initial condition. Assume you have a box of partons as a finite configurations with a high temperature that has a vorticity pointing in the y directions. All right. and has initial opposite angular momentum, huge opposite angular momentum, but no spin polarizations. So that's initially, it's all opposite angular momentum, right? And no spin polarized. All the partons are not polarized, right? Then there's net product means that equal number of the all mass parton, equal number of points in this direction versus the other direction, so they cancel. We don't give a net spin polarizations, right? But as time evolved, then the opposite one goes down, the spin part increases, but total is conserved. So that shows you how to convert. You're also showing you here, right? That's angular momentum. So that's the angular momentum. It's the polarizations, right? So the spin angular momentum, opposite angular momentum, right? The total angular momentum. So you convert this opposite angular momentum into spin angular momentum. Therefore, the polarizations, right? The polarization depends on the spin, so they give the spin polarization. So this spin gives the spin polarization. Right? And from that, well, then he can explain the atmospheric angle dependence of the longitudinal polarization. Just look at this one, right? So look in the rest frame, fluid rest frame, then you see that is the spin one is this one, contributions. The orbital one is this one, and the total is the green one, so that right side. Just like the Even's calculation with kinetic and without conserved total angular momentum during nuclear proton scattering, but somehow they get a similar result. Okay. Of course, most recently, and skip that one, we have heard this new development try to end the spin polarization vector of a fermion. It's pioneered by a paper by Chiral and Ying and others. And later on, also started by Bacattini. Those three papers, right? They're all published about similar times. They said that the spin vector contains two contributions from the fluid. One is the thermal vorticity. That's a thermal vorticity beta is a mu over t. That's a minus. So that in the rest frame, relative case, that is curve of U, curve of V, right? But that's another one. You just change this minus to the plus. That's called the Kc, which is called the thermal shield, and that is related to the quadrupole moment somehow, right? And also probably related to this term as well. Now, based on this new idea introduced, normally in the old calculation of Bacattini or Jung Wang, when they calculate the lambda polarization either along the global and on the y directions or longitudinal along the z direction, they are only including this term, like that term. So after now, and Bao Chi-Fu and Shuai, of course, Ying and Hui Cao, Pan, Nonggang Pan, they including both contribution by using 3+1 music hydrodynamic models calculated right after decoupling, right? So you look at the lambda polarizations, right? That's the don't look at the py, just look pz, right? So without the thermal shield, you get the wrong sign, right? You include it, you get this sign, still not wrong sign. You have to go to positive, get the symmetric experiment. This experiment, positive sign, negative sign, so still wrong. Well, they observe if they don't look at the lambda, they look at the S quark. Right? During decoupling, you just look at the S quark before they convert into lambda. Then somehow S quark has the right phi dependence as a function, right? And that's he called the strange memory. Somehow, if a lambda polarization is entirely determined S quark, well, then you can explain the data. So in that way, and that's what the way shown by Shuai in his side jump of formalism, and also by even in the chirokinetic approach, convert S quark to lambda using quark coalescence model. Of course, here the hydrodynamization not using coalescence model, they're using the Cooper-Frye. So the lambda polarization has nothing to do with S quark polarization. Lambda polarization including doesn't know where they come from, right? That's right, it's still good. So that means that somehow the hydrodynamization cannot be due to those statistical hydrodynamization. Somehow the one needs this kind of quark coalescence pictures. So let's skip the y direction, the global py phi dependence, right? Again, if you look at the S quark, they have a similar sign as experimentally measured, positive. So that's the strange memory scenario of this paper, right? It requires somehow favor quark coalescence model after one includes the thermal shear effect. And this thermal shear must be related to this orbital contribution of Chiral and also maybe Ethan's work over here. Still not quite clear to me yet. Then that's another, at the same time, Picatinny and his could also look at the same the longitudinal polarization by including the thermal shear beside thermal. That's the thermal vorticity with the wrong sign. But once you put thermal shear, it's the upper one. Instead of smoke, see here's a cascade sign, right? And then depending on temperature, if the temperature is 165 and 75, 73, you get the right sign experimentally, but too large. You get 65, you're down to here. You get 150, agrees with data, experiment data perfectly, right? If the decoupling, right? But of course, then there's questions. How can he get this right sign? Hui Chao and her crack cannot get it. They get this one. The reason is Picatinny did introduce another assumption, is that called isothermal local equilibrium of a lambda string polarization. In other words, when calculate this expression here, when they take the derivative, the temperature derivative is taken out. You only take a derivative with the fluid, the velocity, but not the temperature. You have to remove this sign. Remember, I mentioned sometimes ago, this sign. You just remove that one. Then they get to they can also explain the experimental data. And we didn't realize, Picatinny already studied the temperature dependence, but now you go to 133. Suppose the hydro evolution lasts until 133, and then he calculates what's the lambda polarization through Cooper-Frye, converts the fluid into lambda hadrons, then he collected the time dependence of the temperature, then he get this curve again. So then questions, why one complex data at this temperature 150 rather than 133? Because we know that even you stop here, there's an additional hadronic evolution. Will that bring this back to here? So that we start to look at with Yifeng and Zhen Zhang and Wenbin Zhao. And we also do the same thing in music, but we follow with Cooper-Frye plus URQMD. Then we, in the URQM, we follow hadron evolutions and do the coarse graining to calculate the local thermal vorticity and thermal shear, right? And then from there, calculate the lambda polarization. So for the global one, no effect, right? Dominated by thermal vorticity, right? And the thermal shear contribution much smaller, right? Now we also look at the PZ, longitudinal vorticity, longitudinal polarizations. How it depends on the thermal vorticity and thermal shield. That's again we look at that PZ only, right? So this is the thermal vorticity, wrong sign. There's the thermal shield, the right sign. And the total, right? If you see this is very, very small, right? It's very small. And right. They cancel somehow, right? You don't get much, right? And we can also see both sides of the later time of hadron evolutions, right? Go to the 140 MeV, then the total become wrong sign again. So that consistent with Picatinny, right? Picatinny hadron hydro until to that temperature, then to the Cooper fry. We run the hydro at this temperature, then evolve that subsequent method by URQMD, then calculate local thermal vorticity and thermal shield, and also get the wrong side, right? So again, thermal shield may not be able to explain the longitudinal polarization of the lambda, right? So there is questions. What should we do, right? Should we stop at the 160 MeV in hadron collisions and look at the number of polarization, 140, or at the kinetic field? At the kinetic field, you see the Px essentially has no phi dependence, Py has not flat, Pz has a wrong sign, right? So if we stop here, so there's still questions. Of course, there's another questions. In this calculation, we assume the lambda polarization is always in thermal equilibrium with the vorticity and the shield in the thermal medium. But that may not be the case. Maybe somehow lambda polarization freezes out at Tc, then remain the same during the hadron evolution. That's possible. Just like in the statistical hadronization model, all the particle yields fix the chemical freeze out. During the hadronic evolutions, the particle ratio, all the particle ratio, they do not change due to the fugacity. Every hadron develops fugacity. Right? So there must be a mechanism to maintain the hadron, the spin, the polarization of lambda, for the pure global one, right? If free lambda produces a speed determined by 160 degree, that's this magnitude. If you go to 120, 120, then go down by factor 2 or so, right? Then polarization decreases. If you can feed the data with this 9, then you cannot feed data with that 9. So somehow, maybe the lambda polarization freezes out at Tc for some physical reason. That's very interesting to pursue and understand. So I think I'm time's up. So, and then let me just final topic. That somehow I like this topic, but nobody pay attention to it. That's called the multiple up-down asymmetry. We know now there's no signal for chiromagnetic effects. Right, because in order to explain the data, one needs a long-lived magnetic field, which is unreasonable. There's no signal for chiromagnetic effects, all right, because the magnetic field lifetime too short. And now that's another observable does not depend on the magnetic field, depending on vortical field, which has a long lifetime, much longer lifetime. This is so-called the. So if we look at the I'm going to charge particle, positive charge, negative charge, for example. The charge doesn't have to be, if you have a baryon, anti-baryon, for example, charge, anti-charge particle. So we're talking general charge, right? So they have a V2, but they also have this dependent due to chiromagnetic effect, due to magnetic field, right? There's another chirovertical due to omega field. They have a similar effect. Here depend on the charge, right? Depend on the charge, right? Now, since we know there's no chiromagnetic effects, we can drop this one. So we only can study vertical effect. So what's the effect of that one? And because there's a sign phi dependence, then we know what happens, right? So this average value, right? So this measures the average value of these quantities. And that value, let's see, I show what we calculate as a finger time. If there's no initial axial charge fluctuation, or no topological charge in the system fluctuations, then this would be 0. But if that's a finite value, that means that you have axial charge fluctuations, you have topological charge in the system, and then you get this one. That's a very large one. Okay, that's about, again, this is about 1 axial charge per unit volume. It's very large. You get this sign, right? And that's entirely due to the vertical field, right? That's because of the vorticity field. But that's because it has a long lifetime, therefore you can develop that if the initial axial charge fluctuation is large. Right? Then you can look at the how do you measure this effect? You can look at the upside down symmetry distributions and look at the particle move in the upper hemisphere minus particle move lower hemisphere of the reaction plane. That's look at A. Then I construct this distribution. Do the R distribution, we will study chiromagnetic effect, right? We do the instead look at these quantities. So again, we see this typical behavior, right? If the initial is no topological charge fluctuation, that's no axial charge fluctuations, then you get the flat distributions, flat distributions. But if you have a large topological fluctuation in the produced matters, then you have this concave shape. So by measuring this event by event fluctuations of these quantities, one can measure this one. And that once we know this shape, we can measure A. Once we measure A, we can go back to extract this P lambda, that is how large the initial axial charge fluctuation produce the quark matters. So that concludes what I want to talk. So let me summarize. Again, as a magnetic field generating electrons, they are large. We all know they have a lot strongest magnetic field in the universe. Unfortunately, it's probably the shortest lived magnetic field in the universe. And they make it hard to see the chiromagnetic effects because aside the problem, if the topological charge is very small and produce the quark-gluon plasma, then it's also very hard to see the magnetic effect, chiromagnetic effect. And also chiromagnetic wave, right? Shorter magnetic field is very hard to generate chiromagnetic wave. And also chiromagnetic wave destroyed one including consistently the effect Lorentz force in the medium. But on the hand, the vorticity fields, which has much longer lifetime, indeed that is reflected in the lambda polarization measured in experiments. And this part, let me just skip it. I didn't really talk much about it. Of course, from chiromagnetic effect, I have to repeat again, requires a non-magnetic field lifetime and a large topological charge fluctuation of the type of charge, which is not seen experimentally. That's another typo, so the wrong bracket. Longitudinal spin polarization affected by both transverse components of vorticity fields and the thermal shear effect. Unfortunately, one needs to do some additional assumptions in order to explain the longitudinal spin polarization. I think in the kinetic approach, whether with or without side jumps, you can explain the longitudinal spin polarization if the scattering process is large. You want to explain by thermal shear, then one has to make two assumptions: either the strange quark memory assumption of 宋慧超 or the isothermal, how you call it, that is the Picatinny's isothermal local equilibrium scenario to get that sign right. So there's still many things to be studied in order to fully understand why longitudinal spin polarizer have such a at most angle dependence opposite to the at most after the what expected from the V2 of particle flows. Finally, large vorticity fields generated in non-central heavy collision can, that's another typo, can lead to an up-down asymmetry of produced particle if axial charge fluctuations are present in the produced quark-gluon plasma. So I really still do not understand why nobody experimental talk about it, right? It should be a straightforward measurements. You can measure the particle in the upper hemisphere and lower hemisphere after the action plane is determined. Okay, so thank you so much for your attention.
谢谢柯老师为我们详细介绍了关于这个手征方面的手征磁效应啊，还有这个极化一系列的这个研究工作。那下面我想问一下那个线上或者线下的老师同学们有什么问题吗？请大家那个直接提问或者举手，或者是敲在聊天区都可以。王晨老师有问题。
我能问了啊，柯老师，很好的。
王晴啊，你好，你好。
就是我想问一下，你们在做这个CKE， 就是 Chiral kinetic equation 那个模拟的时候啊，你们是你是开放空间呢，还是有一个放在一个盒子里
？Open system， 我们 model heavy collisions， 像孙一峰他有时候用 AMPT 的 general patterns。然后呢，把它送到 Chiral kinetic equation 去 solve 它。
那你这个就是一个自由空间，自由空间的话，它还有扩散啊，什么东西的，这些都在。
Of course。还可以 generate V2 吗？不是我需要可以 generate V2 吗？我看我再回去 share screen 给你啊。不是他 Chiral kinetic 不是这边可以算这个 V2 吗？怎么不动啊？有的，这边。他不算了 V2 吗？他就是
那就是说，如果你放到一个盒子里是不一样的，是吧？
那盒子我们没有
边界条件。
做盒子会达到 equilibrium 啊，这不是那个谁刘帅做一个也不算是盒子，他那个也不算是盒子，他是有点像盒子。刘帅的这个 calculation 在 Let me see 在哪边？在这边。这个刘帅 calculate 对不对？他说他一开始有这个换掉，我送错了对不对？你可以看，我现在我不是在我的那个我现在不能用那个 pointer 的，没有 pointer，开错了 screen。Anyway， 它这是一开始是一个 box， 对不对？很大的一个 box。然后它在 evolve。So basically 它是相当于，你看它看的是相当于，因为它是 size 只有 2 Fermi， 你看吗？这边只有2 Fermi，对不对？所以它根本就是，而且他后来看的是当中，所以它几乎是等于算是个 box calculation 的这个，还是膨胀，但是相当算 box calculation。对。但你如果摆了 box 里，最后达到了 equilibrium values。
但是这个 box 它如果是比如说你放在一个 box 里头，它还有个边界条件的限制，是吧？到了边界
你要这边没有摆，你的 box 要把 periodic boundary condition 摆进去，对不对？你看那个孙一峰不在这边讲吗？他如果摆到 box， 比如我不知道我 check 过没有，可能 check。他如果用这个 modify 这个 phase-based distributions， 他如果摆了 box 来，他就会用这个 prescription 来算这个 two-body collision， 他就会达到他要的那个 equilibrium distribution。我相信他 check 过的，对不对？然后他再用到这个真正 heavy collision， 就是 freely expanding the system。I think it's always a good idea to put a box to check the code to correct it.
好，谢谢，
谢谢你啊。
柯老师，我接着王老师这个问题，咱们那个 AMPT 里面的quark 是没有自旋的，你如果用 AMPT，是不是你就一半的
没有？
自旋
像这个
向
是在那个孙一峰之后，他譬如假设用 AMPT 的 condition 进来，他进到这个 Chiral kinetic equation 的时候呢，他每一个他也没有 follow spin， 因为他的 spin automatically follow 那个 either 是 along P 或者反 P， 因为他是 treat massless case， 对不对？这样 eventually 的话，应该是用这个新的这个 Chiral kinetic equation including explicit 这个 spin， 对不对？
它没有一个
这 spin 不一定 spin not necessarily follow for massive particle spin 不一定 follow 你的那个 momentum direction， 对不对？Right， 这样我们现在是因为做这个 limit assume 是 massless， 所以呢，它真正也没有 follow spin， 它只 follow momentum。但是你知道 momentum 就知道 spin， 如果它是 right-handed spin 就是 pointing along momentum，left-handed 就是它 follow 这个 right-handed left-handed， 这个它有 right-handed bottom。就他进来，从 AMPT 进来，对不对？如果他说一半 right hand 一半 left hand 的 bottoms， 那他就没有 left axial charge。他可以说我有 2% 或 3% 或 5% 的那个 net more right hand than left hand， 他这就有 axial charge distribution， 所以他可以做这个 distribution。这个 on the average 是没有，但是这个 event 要多一点 right hand 的 bottom， 另外一个。多一点 left hand charge， 那是 random 让它 distribution according to 你要的那个 average fluctuation，right？ 那就是 model 你 initial 那个 topological charge 的 fluctuation 一样的，right？
原来是这样。
Yeah. Correct me， 孙玉峰，如果说错什么东西，你 correct me 啊，你知道的 detail，I don't know the details。孙一峰，你在那边吗？孙一峰 ，Hello。
我们这个 CKT 也可以使我们的这个物质热化 thermalization 是吧？如果是传统的 transport 也是 thermalization， 那么是不是 CKT 要会和那个传统的 thermalization 不太一样？传统的 AMPT 的 thermalization 的话，就是好像没有达到那种完全 thermalization。就是
一样的，
这个 CKT，
这个 Chiral 也不见得达到 thermal equilibrium， 但你可以 approximate， 对不对？就像王群不是做 AMPT 吗？他进到那个 after hadronization 之后，他 assume 这个 hadrons are thermalized， 然后做 coarse graining，extract temperature， 然后 calculate the vorticity， 然后他算 omega over t。然后算到随着什么时间变，它就算是 thermal vorticity contribution to number polarizations， 就是说那是一个 probably pretty good approximation， 对不对？因为这么多 collision 在这个 AMPT 你在当中的话，多半是 close to equilibrium。其实呢，在那个孙一峰在算的时候，他有时候assume，因为他有时候为了要达到很大的这个，他要 reproduce， 比如他说A·S，lattice 告诉我们 A·S 怎么 depend on temperature。比如他如果现在用这个 parton scattering 来 reproduce 那个 lattice A·S， 那他就需要 find locally 那个temperature， 对 locally 的 entropy， 然后从那边他去 determine what cross section 他需要用来 model 这个 strongly coupled QGP， 对。但是那不是 exact， 它只是说因为大概是 good approximation， 就是 locally那个 transport model 大概是 close to equilibrium， except on the surface may not be the case。The surface 就不同了，这不是林子维讲的吗？这个 escaping effect 就很重要的 surface， 它不要达到 thermal equilibrium。
好的，谢谢高老师解释。那个我的博物道心里有一个问题啊。
呀。
柯老师。
Yes。
对我还是刚刚这一页，其实有两个问题，一个是这里我看孙一峰做的时候用了那个 isotropic 的一个 scattering， 我不知道你们有没有试过用那个 forward angle 嘛？因为本来 forward angle 的 scattering 也是那个 AMPT default 的一种形式一种情况。
我没讲我没有得到，你再讲一遍，你说什么？是不是在这边？你是想在这边啊？我没有听清楚你讲什么，你问什么？
第6页 page 6。
第6啊，page 6page 6，5、6，这 6啊。
对，
这边啊，
我看这里说的有
这个
用那个说的 6，这页
是的，
对，这里那个说是用 AMPP 的initial
你说这个这边这6咋来的？这个
不是下面就是用 isotropic 的 scattering， 然后来算，就是 pattern cross section 是
10个millibar， 对，
就这2点，就是一个是 isotropic scattering， 就是我没有明白，就是本来就是 AMPP 默认用的是 forward angle 的 scattering， 我不知道你们有没有试着用 forward 来看这个结果，就是结果是怎么样的？
这个当年孙一峰是因为要 reproduce 这个 V2 嘛，如果你用 forward scattering 的话，你的这个你就得不到那么大的 V2。isotropic 不仅要 isotropic， 还有很大的 quarks 你才能得到 V2 correct， 这是他得到。如果你用10 millibar 但是 forward peak 的话，他就得不到，因为你 forward peak 的 momentum transfer 比较小。所以你的 thermalization 就不那么快，你的 V2 就不会 develop 那么大 ，right？ 在 MP 这是个 parameters， 你可以用 isotropic， 你可以 easily go into the code 把它变成 isotropic。
下面
什么的下面什么地方？
对，我的意思是这里就是相当于是用 isotropic 的话，相当于用比较大的这种 cross section， 就是结果会好一些，就是 flow 会大一些嘛。
对不对？如果他现在如果用 forward， 他可能 V2 是这个样子。他用 isotropic 用小 cross section 可能也是这样子，就要 isotropic 要大，你才能这个样子。OK。
但我担心的是这个10 millibar 是不是太大了，在这里是不是合理？
它这个 parameter 它没有 physics， 它就是 modeling 这个 strongly coupled effect， 它要得到 V2， 对不对？然后但是我一定 make sure 就是说他在计算的时候，这个我从来没有去check 它是不是。当你 cross size 一大的时候，你 cross 这个 number of collision 很多的时候 ，one has to be very sure 你的 treat collision algorithm 是不是准？因为你这个有时会 violate causality， 就你 collision 太多了，因为你 go beyond 这个 Boltzmann 那个 model， 可能就是你的那个 mean free path 不能太短，对不对？你 mean 太短的话你就不行了 ，right？那时候你要用 trick， 你要用这所谓的 partition method trick， 但是我不相信我们用了 partition method， 所以这边可能有那个问题，对不对？但one可以解释，就用 partition 方法，就是你每一个 particle replaced by some number of particles， 然后 cross section divided by the like number， 这样你会 artificial 把 the mean free path 变大，就是你要解 Boltzmann equation 原来是要解这个 dilute system， 假设你还是用 Boltzmann equation 来解这个 dense system， 你 equation 写下来，对不对？你说我 somehow 我这个 Boltzmann equation， 但是我的这个 density 很高，要怎么去解它？这是 different， 一个是 physical 问题，一个是这个 mathematical 的问题，对不对？如果你这个 Boltzmann equation for dense system 的话，也许的话你那个 physical 不对，那就是因为你那时候呢，你可能是不仅要有 two body collision， 你可能 three body collision、four body collision、five body 都出来，那没有在 Boltzmann equation 里面。但如果你 collect higher order collisions， 我只有 two body collision， 但你用普通的方法去解它的话呢，你算不准，那你就要用叫 so-called partition method 去解 Boltzmann equation two body collision， 这是两个不同的问题。一个是 Boltzmann equation， 我们讲 Boltzmann 只有 two body collision， 没有 three body， 没有 four body， 这是我们一般的。但是你可以说我 generalize， 如果 density 很高，我可能有 three body collision、four body collisions， 而且 three body collision 可能重要，因为什么？你在 在 near hydrodynamics 差不多 1 parton per cubic Fermi， 如果你到了 early stage of quark-gluon 你可能有10 parton per cubic Fermi， 然后你再看这个 parton 之间的距离，跟它这个你知道 cross section 大概就知道那个 interaction range， 你会发现一个 parton 同时看到5-6个 parton， 4个 parton 3个 parton 一大堆，你为什么它只跟当中一个打，不跟另外一起打？所以你要同时算3个 parton collision， 4个 parton collision。当年上海大学的那个谁叫什么名字？忘掉名字，好久没见他了。
李小明
啊，马国亮，你可以提我。上海大学也刘晓明，对，刘晓明，他当年 study 对，刘晓明是不是？
徐晓明，
对，徐晓明，他当年写了好几篇 paper 讨论 3 quark scattering。3 gluon scattering， 他发现 effect 很大在 QGP， 当然人家都不 pay attention to， 因为他就用普通这种方法做，也没有去 worry 这个是不是 consistent 的这个power counting 等等，他没有去看，他就是画着 Feynman diagram， 引发三个 coupling， 他就去算，发现因为 density 高，所以那个很重要，他就写了些 paper 说，尤其加到3 body collision 就会 make the equilibration 非常快，对不对？非常快。但如果 density 高，可能 4 body 也很重要的，4 body 的 nobody 会算，5 body 更不可能的，那个难的。所以到了某个 limit 的话，这个 kinetic approach 呢，就 have to convert it into hydro approach. But the definitely hydro approach is a more convenient way treating 这个 dense system. Right?
好，谢谢裴老师。
谢谢。
还有什么问题？大家有什么问题？其他问题吗？
国亮，柯老师，我还有一个问题啊，就是你在模拟这个 CKE 的时候啊，你那个 collision term 你是怎么处理的
？collision term，
因为你想想，那个左手右手，它有可能它要湮灭，或者说怎么，互相转换，这个你这个有个 collision term。
你就 follow 嘛，就说他像那个孙玉峰他做对不对？我比如有一大堆巴掌，我同时 propagate 它，对不对？2个巴掌 close，他就让他打，对不对？打完之后呢，你决定他 final。
你撞的时候，你有个 collision term， 你那个是怎么？
那个 standard treat transport standard 为什么 treat two body collision？ 像我们这种 two body collisions， 对不对？那普通都是用 geometric 方法，但是 for the pattern phase 大概不应该用 geometric 方法，应该用 stochastic 方法。这个的话，你最好去跟徐哲，他是专家。
不是，这样就是你分辨你在碰撞的时候，你不是要分辨左手和右手吗？
对，这个，对，这个我们那个在第一篇 paper 写的时候，我们 force 他说要这个chirality flipping 这个 scattering， 咱们好 force 他 in order to lead to 这个 charge separations， 产生这个 dipole moment， force 他。这个边我们没有仔细去讨论 theoretical basis，
那也就是说你
应该去算
碰的时候，你不分辨它的左右还是什么？还分辨它的左右？
我们分辨左右的，只是说是，如果是 elastic collision， 就是还是保留原来的 helicity， 如果是湮灭过程，就是 helicity 可以翻转。
就是你是分辨的，实际上还是在这个碰撞的时候啊，你是要分辨它是左手还是右手的，是吧？
对，然后只要保证总的 helicity 守恒就行。
就是说，如果是这个弹性碰撞的话，你是保持它的 helicity 的，是吧？
对，
没有 flip，
没有。
OK， 好，谢谢。
柯老师，还有一个问题，就是您的这个结果里面，好像就是有这个形成极化的时间比那个形成 CFW 的时间要短，这个怎么理解？
你知道什么地方没听懂？再讲一遍。
就是我看到你有一个这个形成极化的有一个时间，quark形成极化有个时间很快的，然后就，但是形成 CFW 需要一个很长的时间。那为什么 就是形成这个极化，就很短的时间就可以。
因为 vortical field 的 lifetime 很长啊，所以它会慢慢一直增加。你这个来，如果我们在孙一峰在算那个 chiral magnetic effect， 它也是 assume magnetic field lifetime 很长 ，chiral magnetic 它也 assume magnetic field 很长，6个Fermi/c， 所以可以慢慢develop 这个 charge separation， 对不对？不是那个 V2 splitting， 但是跟那个 lifetime 有关系。
这个的话，你是那个就是磁场是一个恒定的量，对不对？磁场是
对，在算磁场的，在磁场的计算是 assume 这个磁场，有些时候是 no， 它是 parameterized by 那个一个，我再给你，等等啊，我修给你。
我就不理解，就是为什么同样是 CKT 这个串套这个理论，但是如果是
你看得到吗？你看得到哈？它就是孙一峰这样子的，对不对？譬如你在这个地方，这个公式在这边，对不对？这个公式，它把这个 tau p， 对不对？应该是 0.06， 他说变成6个分米，或者 0.6个分米，
那个 P
就把这个东西拉长就是了。这孙一峰就是把这个 TB 变大一点，叫做 TB 用 0.6， 这个是那个廖金凤这么做，他把这个 TB 变成 0.6。
OK， 所以说我们这个 CMW 需要的时间长，是因为这个磁场是在衰减的。如果这个极化需要的时间形成的
极化的话是自己决定的，他没有动任何手脚，你自己打嘛，因为你一开始打那个 vortical field 就在那边嘛，就打出来了，
好像这个和这个答案也有关系，你有两种答法。
这就是 MTD， 这不是林子维算的吗？这是 vortical field first time 这是算出来的，但 lifetime 很长，所以这 vortical 很好，你用不着。
我讲还最后一。您那个就是说，这个 vorticity 是通过碰撞产生的嘛？然后这个碰撞的话有两种碰撞，是不是？有一个叫 normal 的 collision， 还有一种叫 revised 的 collision。这两种碰撞的话产生的这个速度不一样，是吗？
不，它只有一种 collision 啊，怎么两种 collision？就是因为你打来进去之后，就 automatically orbital momentum， 对不对？这回还是 orbital motion， 跟 spin 没有关系的。这个 omega 都是 orbital motion， 一点跟 spin 没有关系 ，right？ 所以这是 NPD 算出来的， right？ 所以在孙一峰他做的时候，对不对？如果他用 NPD 的确摆进去，我现在不记得他是不是这么做，把孙一峰摆进去，丢到了 chiral kinetic equation 有这个 follow 这个equations 的 vortical field 这个 equation 的时候，对不对？它就自然会 generate， 来，它就自然会 generate modify 这个 p hat 的 direction 把它 polarize。
但是这个 CKT 这个理论里边不包含相变是吧？
没有，他现在没有讨论，他只用到 Platonic phase。assume 整个 Platonic phase 都 described by 这个 chiral kinetic equations， 对，就是说它的 NPD pattern 进来，他把这些 pattern 呢，把它分成多少 right-handed， 多少 left-handed，assume 它 mass 都是0，然后去解这个 equation， 对，either 这个 equation 或者这个 equations， 然后再加上这个 collisions， 然后它就 evolve to system， 它就可以看到这个每个 particle 的 momentum 怎么变？你知道 momentum， 你就知道它的 spin direction。
就我对这和这个磁场的话，会影响相变温度是吧？
这个没有讨论，我们这没有讨论。这个磁场跟相变没有关系。这磁场啊，因为你磁场这到 lifetime 很小，你即使用 0.6， 对不对？像那个孙一峰有的时候 0.6， 对不对？即使这边用 0.6， 到那时候呢，你的黑状来信也很远了。黑状来信差不多5-6个 Fermi， 对不对 ？over c， 所以你在 hydrodynamics 之前，你的那个 magnetic field 已经不见。所以为什么他在算的 chiral magnetic effect 的时候生意？所以他这边他这个是当然用的长，他这个手摆进去，他 assume 的 lifetime 是6个分，有的很长，所以到这边，但实际上到不了那么多，对不对？然后他再继续算，看这边没有他们就选另外一个他们，到这边对不对？他这边但没有 magnetic field，这边是 omega field， 对不对？到这边的时候 omega field 已经很小，对不对？这样会很大。
有一个 revised collision， 还有一个 normal collision， 就这张图。
哦，你说这个啊？
对，
这个是 normal collision， 就是他没有那个 modified 的那个 phase space distribution， 这边不，你那个要 correct by 那个再回到这边给你这边，对不对？他要 modify 这个东西。因为你现在这个 phase space distribution 不是讨论，比如这个 FP 我们用假设 Boltzmann distribution 举个例子，不要讨论 Fermi-Dirac， 这是 Boltzmann distribution， 你要乘上一个这个 factors， 然后你在算 probability 的时候呢，它某个 direction 的 probability 要用这个算，对不对？就somehow这个 enhance 这个那个 collisional effect， 所以这边出来了。
这个为什么 modify？ 是因为我们要满足这个 momentum conservation， 是吧
？momentum conserved， 对。所以说，也许你再可能加一句，你可能解释更清楚，为什么这两个会差这么多？所以说 ，Hello，
没事啊，在。
为什么 normal collision 给的那个 polarization 要小很多很多，比这个 revised collision？
normal collision 就是 cross section 是 isotropic 的，而这个 polarization 只是因为你用那个什么 vortical 把那个粒子分到上下两部分，然后就是把那个什么 XO
charge。square G help， 你知道 square G help 是不是那个 help？
对，就是运动方程里面，它对跟 helicity 有关，然后把上下两部分的那个 XO charge 分开之后，然后导致
这有关系，对不对？这个东西
对，就是 dx dt 这个，就是 normal collision 是 dx dt 的贡献。
dx dt。dx
over dt 就这个运动方程。
这个。
对。
这个肯定没有关系啊。
它是没有关系，但是它是通过首先是那个运动方程让那个 helicity 不同的粒子，一个在系统的上边，一个在下边，然后就是因为 vorticity， 然后再因为它的 momentum 上下不一样，所以导致有一个 global 的 polarization。
哦，那个是 polarization， 对。
对，这是一个慢慢产生的过程。另外那个 modified collision 就是直接在 collision 里面改变，不是 isotropic 了，最后就会很快的让它 polarize。
我觉得用这个 revised 的 collision 呢，会 help 你这个。你不是你那个 dx dt 是 CKE 嘛？
对 CKE。
但是你这个 difference CKE 在这个也有，这边也有，都有 CKE， 但这个 collision effect 大。
对 ，collision 就是相当于是 thermal equilibrium 的一个那个线嘛 ，limit， 就是即使粒子没有，比如在一个 box 里面，那你这个 CKE 的 effect 就会看不到了，就是因为它总是一个 periodic 的，但是这个 reverse， 但是它还是有 polarization， 就是通过这个 collision 导致的。
好的，谢谢一峰。好，那今天这个报告就到这里。